So hi guys. Today I'm going to solve this NBHM 2025 problem. Question number 5, 6, and 7. I think this is from part A, as you can see, I guess. So let us start with this easy question. It is saying that let S11 with the symmetric group on 11 letters. Okay. Let me start with question number 6 first. How many subgroups of order 11 are there in S11? So, like H is a subgroup of G where order of H is 11, right? Order of H is 11. So since this is prime, so H is cyclic. Okay. Now we know there's a formula for finding uh, cyclic subgroup of particular order. Okay. So so basically, so total number of subgroup of order 11 is nothing but this is phi 11 and um, total number of elements total number of elements of order 11, right? Now okay, now basically total now since 11 is prime, so basically like since this is in S11, so let's say sigma belongs to S11, so basically we will have the cycle like of length 11, because only a cycle of length 11 will have a order of 11, right? Because since 11 is prime. Okay. So yeah, now if it was some other order, then for that we need to find the partition and the decomposition. For instance, say we need to find the element of order 8. We know how to do it, right? 4 plus 2 plus 2. One cycle type can be like this. One can be like, yeah. I mean I mean not 4. The LCM should be that, but yeah. Yeah, you get my point. So um, 6, let's say 6. So 3 and 2, one cycle type. And okay, so also 6, one cycle type. So, but in this case, since we need to find the elements of order 11, we can just, um, we can just find the total number of elements. So cycle length is 11, which is nothing but 11 factorial, okay, by 11 into 11 minus 11 factorial, which is nothing but 11 factorial by 11 into 0 factorial, which is 1. So this will be 10 factorial. So let me name this one. From 1, we see total number of subgroups of order 11 is 10, 10 factorial by phi of 11 is 10. Phi of p is p minus 1, where p is prime. So this is nothing but 9 factorial, which is our answer. Okay, so this was okay. So the answer is 9 factorial. Now let us try another question. Now this is a pretty nice question. Uh, I mean, Let me read the question first. It says that for n greater than equals to 1, let Sn denote the set of all permutations. Okay, so basically it's a symmetric group of order n. Order n factorial. So um, let Pn denote the probability of the event that a randomly chosen permutation does not fix any integer in its original position. Find limit n tends to infinity Pn. So basically, they are like asking us to, they are like telling us to find the total number of, if we are able to find the total number of D arrangements, okay, then we are done. By that, let me explain this further a bit. So in the question, it says that a randomly chosen permutation does not fix any integer in its original position. Okay, so for instance, let's say n equals to, let's say 4. So let's say we have boxes number 1, 2, 3, 4. Now we want to arrange in such a way the letters, I mean, suppose this is a blank named 1, blank named 2, 3, and 4. We want to um, uh, like permute in such a way such that none of the original 1, 2, 3, 4 gets in their places, right? For instance, I can do 2 here, 1 here, 4 here, and 3 here. Okay. Or maybe I can do, let's say 1, 2, 3, 4. Let's say I can do 4 here, 3 here, 2 here, 1 here. So yeah, none of them are in their original places, right? So so this thing is called the total number of dearrangements. So and there's a formula for it. We also denote total number of dearrangements of n by this, and this is known as a subfactorial. Okay, so this is known as a subfactorial, and this will be the formula is like this. I mean the proof is also very nice. Um, so the formula is this summation I 0 to n minus 1 to the power I by I factorial. Okay, so this is the formula. Now this is the total number of dearrangements, and they are asking us to find the probability. So probability of that particular event. So let that event we denote E to be the particular event. mhm, To be the particular event. Now probability of E happening is n factorial um, mm, I 0 to n minus 1 to the power I by I factorial by n factorial because the total number of permutations is n factorial, right? Yeah, so we denote it by Pn. Now this is so yeah, so this is nothing but Pn. So this will be nothing but minus 1 to the power I factorial. Now again limit n tends to infinity P of n is as we know that limit n tends to infinity and we know this, right? This is a common series, so this is 1 by e to the power minus 1. Okay, so answer is e to the power minus 1. So this is a pretty nice question. I mean, if you know the formula for dearrangements, then it's actually very easy. But yeah, so this is 1 by e. So this is done. Now we move on to question I think 5. This is a pretty nice, interesting question. Uh, now basically they are saying that yeah, so basically in question number 5, they're saying given a metric D on R square, the closed unit ball around 0, 0 with respect to D. Yeah, basically they have defined closed unit ball. If D is induced by a norm, then which of the following shape can the closed unit ball around 0, 0 with respect to D take? Okay, so this is an MSQ type. I mean multiple correct, more than one can be correct, all can be correct. Okay, so yeah, so basically they're saying like you have a we have a norm and we have a metric induced by that norm. Now what can the closed unit ball, I mean, what type of shapes the closed unit ball can take with respect to D? So so yeah, so first option is rectangle, second option is ellipse, C is equilateral triangle, D is a parallelogram that is not a rectangle. Okay. Now now parallelogram that is not a rectangle. I mean, yeah, I mean a rhombus, and we know, right, and we know, and this will be true because, I mean, this will be true because, of course, this will be true because, of course, like, uh, now we can. This is a parallelogram, but this is not a. This is a parallelogram which is not a rectangle. It's a rhombus, right? So basically, the norm. I mean, let's say is x comma y. I mean x1. Um, let's say x1 y1. Then this I think it's called the yeah norm 1. So this will be plus y something like that, right? So we will get this shape. Okay, yeah. So we will get a rhombus because right, we want a closed unit wall, right? So basically less than equals to 1. So we will have like this. And we know this is a very common shape. So this will give us this figure. This is a parallelogram, which is not a rectangle. So this is easy. Now for what about an ellipse? Can we have an ellipse? So for that, we want an ellipse. So let me first, let's say this r square with a usual norm, right? By 2, I mean the usual norm, that is x1 squared plus root over x1 squared plus y square. So we do a map from, I mean, this is a norm, I mean, this is a finite dimensional non-linear space, and we have not defined a norm for this yet. Okay, this is a vector space, obviously. Okay, now we define a linear transformation like this. Okay, so I mean, I'm just writing the metric. I'm just writing the metric. So basically, so for in this norm, in the this norm, a closed unit ball will look like this, of course, right? This is a circle. Oh my God, such a bad circle. Okay, yeah, a circle will look like this. Now, using a linear transformation, we want to make it an ellipse. Okay, so okay, this is a unit circle. So this is our 1 comma 0. I mean, or E1. This is our 0 comma 1 or E2. So like if we stretch it like a times and if we stretch it b times, we will get an ellipse, right? This will transform into an ellipse. Basically, we are sending E1 to, let me write it here, A0 and E2 to 0b. So this is our linear transformation. Okay. So xy will give us ax, ax and by. Okay. So this is our t, right? T of x comma y is this. All right. Now, yeah. So yeah, so this is our so basically now we are defining, now this is a linear transformation. Of course, this is, and of course a unequal 0, right? So as we can see that this will be a, I mean, rank 2 matrix. This is invertible, right? So basically we have a bijection. Uh, this is invertible. Basically we have a bijection. Now on R square we, let's say, define let's say 3, a norm like this. I mean, okay. I mean, the on the image part, right? We define a norm like this. So let's say x belongs to uh, r square, and here x is, let's say, x2 y2. Okay. Let's say x is here, x belongs to, then norm of x3. We define it as t inverse x. We define it as t inverse x. Right. Okay, and this, and we can check that the new norm we have defined here is, I mean, is actually a norm, and we can easily see that, and this will be an isometry, right? So yeah, so we have defined, basically we are transferring a structure. We have a norm linear space, we have a vector space. Now since there is a bijection, we have transferred the inner product, I mean, or the norm here in this case. Okay, so basically we are transferring a structure. So we have defined a norm here, which is this. Okay, so now, and now what is T inverse? Uh, yeah, so we have defined a norm here. Yeah, so I've defined a norm here. Okay, we have transferred the structure. Now one more thing. So what is T inverse? Then T inverse will be 1 by A 0 0 1 by B. And now notice one thing. Okay, then so basically it will be, so this will be, I mean, so this is nothing but x1, sorry, x2 y2. This will be uh, t inverse x1 y1, right? Okay, norm 2. Okay, now what is t inverse? uh, Sorry, yeah, I mean, yeah, sorry, this is t inverse x2 y2, which is nothing but x1 y1, okay, where t of x1 y1 হচ্ছে uh, x2 y2, right? I mean the image, the pre-image. So okay, so um, now this is nothing but, yeah, so basically this will be this. So basically, I mean actually we don't need this. So and we know this is, since we know what T inverse is, right? T inverse is this. So x2 y2, this will give us x2 by a and y2 by b, right? So this will be x2 by a, y2 by b, okay, and norm of in the usual norm, which is nothing but x2 square by a square, y2 square by b square equals to, yeah, yeah. So yeah, so basically we get an ellipse, right? So we get an ellipse. Now, I mean, this is the intuition, right? That we are stretching E1 by A times and stretching B1, I mean E2 by B times, right? So like this, the image we will get stretched like this. I mean, semi-major and semi-minor axis. So something like this. And depending on A and B, it can be this type of ellipse as well, horizontal or vertical ellipse. Okay, but it's depending on, but it will be an ellipse, right? This is a yeah, and this is B. Basically, we are stretching the whole thing, and we can easily see from here, like if we, let's say, if this is less than equals to 1, right? Then this is 1, and we can say that x square by a square plus y square by b square less than equals to 1. So the summary is we have a nonlinear space with a usual norm r square with the usual norm, and we are having a linear transformation from one space to r square. Now here r square, there is only the vector space structure. We have not defined any structure yet. Okay. Now since T is a bijection, we will have we can transfer the structure of r square, I mean with the usual norm to here. Okay, and we have defined a new norm like this, and we can see that this will be a, yeah, isometry. So okay, so there will be a nonlinear space isomorphism between the two. So we have defined a new norm like this, and we easily see that if we stretch the circle, we will get an ellipse. Okay, all right. Now we can, yeah. So this is the main point, that we are defining or adding a structure in such a way that our circle is getting transformed into an ellipse. Okay, while maintaining the injectiveness, bijectiveness, or the while maintaining the structure, while not disturbing the structure between the two. Okay, all right. We have isometry. Uh, yeah. So okay, so this is done. So yeah, so this is the concept. I don't think I did a good job of explaining this correctly, but yeah. So this is a parallel. So this is okay. So we will get an ellipse. Basically, we will once again have a bijective linear transformation, which stretches this a circle to an ellipse. Okay. Now, will we get a rectangle? I mean, I think we will get a rectangle because, I mean, what about the soup norm? Okay, so basically we'll use the same concept. We will use the soup norm. Okay, that is, let's say max of x soup, or I mean the soup norm, or the, I think it's called, sorry, I think it's called the, I mean infinity. Yeah, infinity norm. Sorry. So it will be maximum of x1 y1, mod of x1 y1. Right? So for this we will get a square. I mean in this norm we will get a square. Okay. Now one thing we notice, that since we will get a square, so this is our E1, okay, and this is our E2. So what linear transformation, bijective linear transformation should we take so that we can imbue a structure in R square? So basically, okay, let me write this. Let me not. Uh, yeah. So basically, similarly, we take r square with the infinity norm. Okay. God damn, what am I writing? Yeah, with the infinity norm to r square. We have not given any structure to it yet. Okay, we will define a norm. So 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 we will have a matrix 1 0 and let's say 0, let's say 2. Okay, this will give us a rectangle because in the soup norm we have this square. Okay, now using T, a bijective linear transformation, we will imbue. So E1, so in this case, X and Y, okay. So E1 will go to E1, right? So that is not a problem. And what about E2? We will stretch E2 by some number. Let's say 2. So this will be like this, a rectangle, okay. And so we can define a new norm here. Let's say something infinity dash, something like that, such that x infinity dash is nothing but, since it's a bijection, we will always have a pre-image tx, right? And under the soup norm, this is our new norm here. So in this norm, our square will look like a rectangle. So basically, we are transferring a structure in such a way, or we are defining a new norm with the help of a previous norm, okay, in such a way that with the help of a linear bijective linear transformation or isometry, okay, um, yeah, so we are able to make the square into a rectangle. Or now even we can actually, we can also, like, let's say we have a square, right? This, right? We can also make a parallelogram which is not a rectangle by sending E1 to E1 and E2 to a particular, let's say, slight angle like this. Okay. So, and we have to check that if it is bijective or not, and so on and so forth. Okay. So, yeah, this is how we generate new norm in a, if we have a bijection between one nonlinear space and one normal vector space. This is how we generate a new norm. Okay, so okay, so rectangle is also fine. What about an equilateral triangle? Now notice one thing that, so basically they're asking for equilateral triangle. Now notice one thing, the fact that, like, if you have a norm here, this is nothing but this, right? So yeah, so uh, so we have a norm like, so this, I mean, norm of x is nothing but, so there is a symmetry. There is a central symmetry. For instance, a circle, I mean 180-degree central symmetry, right? If x belongs to, or the closed unit on minus x will also belong to that. Okay, so there is a 180-degree, you know, there is a 180-degree symmetry, I mean central symmetry. Okay, so but in the case of a equilateral triangle, in case of a, let's say, equilateral triangle, let's say we have this, it's this. So this is 120 degree. Each of them is 120 degree. Now this is not 180 degree centrally symmetric, right? So if we rotate it by, let's say, here by 120 degree, we will get the same shape. Okay. But if we rotate it by 180 degree, we won't get the same shape. Okay. So this won't form a metric. Won't form a metric. Okay. So we won't have a closed, ever equilateral triangle as a closed unit ball, right? Okay. So yeah, so basically we are done. So this will be false.